Let me shortly introduce myself. My name is Pavel. I'm from Kaspersky ICS CERT. My daily job is to find vulnerabilities in SCADA software. And in the evening, sometimes I do my own personal research. A little bit about my discoveries in the past. So on this slide, in 2016, I made quite a successful bug bounty story with my friend and colleague Emil Lerner. I found several critical vulnerabilities in FFmpeg by using a technique that we will be discussing today. In 2019, I discovered around 50 vulnerabilities, maybe more, in remote desktop access tools, majorly VNC. I utilized fuzzing during this process as well. And this summer, I have been writing a blog post about my discovery of several vulnerabilities in VirtualBox. And during this process, I utilized automation of memory corruption bug findings as well. So several prerequisites for this little workshop. So I think you should have a common sense what memory corruption bugs are and what undefined behavior is, like common stack overflows, use of the freeze, and you should have some experience in C or C++ development. I think this talk would be interesting for software developers who are looking for some tips to secure their software, and security researchers to help others to secure the software all around the world. And maybe for the students, this would be a very interesting theoretical subject as well. So in today's talk, I would cover a brief history of fuzzing very shortly. We will talk about various ways of fuzzing software, about the tooling, about the tips and tricks. And in the end, I would give you some homework, which would be a practical part of our workshop. Unfortunately, I didn't manage to have an exercise that would fit 50 minutes or less. So I decided to give you a homework, and you would be able to reach me out on Twitter or by email anyways. Okay, so let's start. If you would go to some software design course, you would have some diagram like this, which consisting of 5 steps. And the fourth one, which is usually called verification, I call it testing for now, because not to confuse with verification, software formal verification theory, which is quite a complex mathematical subject. And today we will be discussing the process of implementation and testing software majorly. Let's move on. So first of all, the first obvious step, how testing software was implemented, is by writing unit tests. So while writing a C code or C++ code, you don't want to break your software during making some changes. So you implement some tests, and it's kind of an invariant that should be always tested. And when you are deploying your software to production, you should run tests, because they verify that you didn't break anything by making some changes into your software during the latest commits to it. But sometimes you may come up with a problem like this. So let's assume you have a buffer allocation process over here. And as you may see, so assuming that this is a networking application, you may have a free kind of errors in just 2 lines of code. So assuming remote attacker may control size 32, it may overflow, and it will result to the buffer overflow later on during the call to read function. So the return value of malloc is not checked, and return value of read is not checked, which could lead to null pointer dereference and to usage of uninitialized memory correspondingly. So to find problems like this, static analysis was created, and the simplest example of static analysis, I think, is compiler checks. So compiler can check easy stuff like this, that you haven't used return value of read function. But the problems are getting more complex with time, and static analysis tools are getting more complex as well to find them. So latest static analysis tools are supporting stuff like you can write a query to your own code to discover some kind of pattern, or this pattern, in example, it could be a vulnerability in the software. So, but today we will be discussing majorly the third approach to find and fix, to find defects in your software. So someday one person came out with the idea, what would happen if we test our software with just piping some random data into our program? Because sometimes it has broke just by receiving some invalid or random data inside it. So let's just try to test it that way. So, and this is how dynamic analysis was created. And it is the term fuzzing was coined that in that moment. So the term fuzzing comes down to the infinite monkey theorem. It is a mind experiment when you have infinite amount of monkeys typing randomly on a keyboard, and as a result of this experiment, they in infinite time they would type any given text. So this is the concept which we would be using during the process of fuzzing. So we have some input, and it goes into some magic process, which is called our fuzzing engine, and we receive some output that we would pipe inside our program, and later on we expect this program to crash. Not necessarily, but it may crash. Okay, so input is optional, as you have seen on the previous slide, because there are two major strategies for fuzzing data. Mutation and generation. Let's cover generation first. So as an example, I would use a very popular vulnerability, I would say, found by a very talented researcher, and it is located inside a JavaScript core engine, which is used in WebKit as an example. So it is a JavaScript processor, and let's see what happens here. So this is the code that triggers the bug. So here is some array which has been created first. Here is some cycle which is populating this array, and there is some weird object with weird process, with weird property, and a function call, and this results a memory corruption bug. So how we detect bugs like this? So to detect those, we would use a theoretical concept which is called formal languages and grammars. So let's assume, as an example, that we have this kind of language, and the grammar actually it is four objects inside this grammar. T stands for terminals, N stands for no terminals, P production rules, and S is the starting symbol. So the grammar actually is trying to generate all languages, all words inside our language. And it tries to do it by using these production rules, which determine the language itself, and non-terminals. So it expands each non-terminal starting from our starting symbol S into all other words of the language. Obviously, in case of JavaScript, which subject would be much more complex. So we have some starting symbol, and let's assume we want to generate the code which we have been looking previously. So the statement start statement may expand into some statement one and variable definition, and let's say it expands into the variable definition, and so there are some non-terminals called var name and some non-terminal called expression, and we have to expand it as well. So there is some next statement which would be expanded, which could theoretically be expanded into the for statement. There are other options as well, but this time it would expand into the for statement. Okay, so now we have our, let's assume we have now variable declaration and for statement, and the process will continue expanding these non-terminals until we potentially could result with a code like this. So this type of fuzzing of generating JavaScript code actually has some problems, but a lot of memory corruption vulnerabilities inside browsers, inside JavaScript engines have been discovered by using this. To learn more about how fuzzers work, I would recommend reading their source code. This is really a good way to learn fuzzing. So a very popular fuzzers at Harma by Mozilla and Demata by a researcher from Google. I think I would share with you, I would be able to share with you slides later on. So these links are all clickable, and you would be able to reach the links that I have linked here. But for now, let's just stick with the presentation. If you want to find them right now, you just you can Google it by using keywords. So what kind of improvements can be made to the fuzzers like this? To read about these improvements, first of all, this is a really common concept, which is called fuzzer as virtual machine, but it was formalized quite not so long ago, I guess. And I would recommend reading through this source code of the fuzzer. There is actually two fuzzers, F0 and F1, which is F1 is described by this paper from German university. And I think that this is a good example how you may speed up the process of fuzzing in a way by implementing it as a virtual machine that builds the code that would be interpreted. So another question is that if you have some recursion in your grammar, how do you solve it? How do you solve the probabilities of the nodes on each of the non-terminal expansion step? So this is a really complex question, and it can be solved in different ways. But this is some subject to think about yourself. And coverage. Obviously, you can collect coverage, which part of the code has been covered. We will be talking about the code coverage techniques today as well later on. But for now, let's just say that you may collect some pieces of code that have been covered by your fuzzer, and you may guide your fuzzer towards covering more and more interesting parts of code. Aspect preserving mutation is a very interesting paper made by Georgian University, George Tech University, and the term aspect refers to some property of the code, some property of the code which you want to keep during mutations of the JavaScript code. And last but not least is the fuzzer made by sælo, a researcher whose vulnerability we have been covering already today. And I would recommend looking into it as well. It is aimed towards finding memory corruption bugs in JIT, JavaScript engine. So this is a very interesting read. And if you go to the GitHub repository of Fuzzily, you would be able to find thesis of sælo, which is a very good read. I would recommend you reading through it. It is quite interesting. So when you think about the process of fuzzing, if you already know what this is, sometimes you remember what generic fuzzers are, like Redemption, which have some generic mutations, but they don't collect coverage. They flip bits, flip bytes. They input some interesting numbers. They do tokenization of text and XML, and they insert some interesting mutations of the text sometimes. But if you have code like this, so C is an array of bytes, and if 4 first letters are fuzz, then some software bug would be triggered, and we would like to detect those. Those generic fuzzers would be never able to discover bugs like this because they don't. It doesn't matter for them that first they don't have a way to detect if this part of the code has been covered or not, or the second line of the code has been covered or not. They are just simple fuzzers that flip bytes. But in about 2012, a new invention has been made, which became very popular, which is called AFL fuzzer. And AFL-based fuzzers, but AFL was the first one, the parent of all those fuzzers. So normally, if you compile this code without optimization, you would have some call graph looking like this. So the first basic block is checking if the first letter is F, and if it is F, it jumps to the green branch, and the second letter is checked. It is compared to the byte U. But if inside first basic block the check didn't succeed, we would go to the red branch, and we would just leave this checking function. So what this fuzzer do? It marks every basic block with some instructions. So it would be able to detect new basic blocks have been covered by mutated input. And let's assume that the input 4 letters A have been passed to this program inside array C, and that way AFL would be able to detect that these 2 blocks have been covered. If it flips a byte and a new letter would be the first letter would be a letter D right now. So the same path would be covered inside the code, and it would be able to detect it. But if it flips a bit inside the text one more time, the letter would become letter F, and a new basic block has been covered, and AFL would be actually able to detect this. So this is called technique called coverage guided fuzzing, and later on it would be able to find all these 4 letters, and it would be able to trigger the bug. It works not exactly like I have discovered, but this is just to give you a common sense how it works. So let me just check a question really quick, and the chat. Oh, excuse me. So there are five messages in the chat that I'm not able to see, unfortunately. Sorry. Let's continue. So the most well-known fuzzers, coverage-guided fuzzers, are AFL and Libfuzzer. So Libfuzzer is actually based on AFL, but they have some differences. Like Libfuzzer is becoming more popular due to the fact that it is now embedded inside LLVM engine, and it works quite well with LLVM compiler, LLVM coverage, and AFL is a standalone project. Libfuzzer is also an in-process fuzzer. Meanwhile, AFL is a fuzzer which starts for each fuzzing input. It starts a new process. So to supply new input, it would start a new process and give it a new input. While Libfuzzer works faster. This is a subject to argue, but from my point of view, it works faster due to the fact that it has one process and it performs the fuzzing inside one process without any need of new threads or new processes to be run. So it speeds up this quite a lot. So why did these fuzzers become so popular? So the first point I would like to make that AFL and Libfuzzer, they are extremely easy to use. You may start fuzzing in minutes. The application that is simply consuming some bytes and performs some parsing of the data, you may start fuzzing in minutes. You have just compile AFL, set it up, and you are ready to go. The second point is, although this software is a majorly collection of hacks, which came up to be working somehow, they're real masterpieces. By learning these hacks, you may become a real guru in internals of different aspects of computer science, like compiler internals, OS internals, hardware and CPU internals and how it works, and so on. One thing that I would like to tell you about that helps us really a lot to detect memory corruption bugs is address sanitizer. It is a tool that allows you to detect memory corruption errors. So normally, if you have code like this, so here you have some 2 pointers, pointer Q and pointer P, and here you are reading from the pointer P and you are writing to pointer Q. So address sanitizer actually works along with the compiler. It allows you to perform some checks on a runtime stage that no out of bounds memory have been accessed. Like it prior to accessing the memory, it inserts some read and write checks and to check if the memory being accessed is valid. So normally you would have to, if you have 2 pointers to ints on the heap, which is weird by the way, but let's keep it for now. You would have something like this. So here you have some 4 bytes and 4 bytes. If you compile your project with address sanitizer, it would look something like this. So here you have the same 4 bytes, but some memory guards have been inserted inside your program. So if you do a memory access to these 4 bytes, it is okay. Address sanitizer during some check read function would go to the memory map, and memory map that will tell that this area is not guarded and everything is okay. But if you would try to access a memory like this during memcopy function or during just pointer dereference, here is probably impossible, but during some function call as an example. So the address sanitizer would go to the memory map. It would detect that this area is guarded, and it would actually not allow you to access this memory, and it would trigger the exception in runtime, which helps us to detect that out of bounds access has been detected during the runtime. So I cannot stress this more, but reading about these tools is super important. These are really great tools. They have a lot of information about their internals on GitHub. So be sure to learn how they work, because it will help you in your daily fuzzing routines. So to stress that, I would also demonstrate a very neat trick by my friend Emil, who is author of gifoeb. I don't know what this title stands for, but actually this is an exploit that he made, which became a very interesting bug bounty story as well. It is an story about how he found and how he exploited uninitialized memory in various services to find usage of initialized memory, and he took over this initialized usage to dump some memory keys from the server. So he uploaded a GIF payload, and as a result, it was processed by the tool which is called graphics magic or image magic. There are two versions of it, and they converted a picture to. They're used inside the cloud to convert pictures and to zip them into some format which doesn't require too much memory. In example, they could be converted. If you upload some image to the cloud, it may be converted to the from GIF to JPEG to keep some space with a very bad quality of the picture. So inside this tool, he was actually able to find a bug, and I will right now demonstrate to you the trick that he has demonstrated once to me, how he has found this kind of vulnerability by using a bash one-liner almost, but this was kind of a bash one-liner. So you can do it by yourself. You can actually download some old version of image or graphics magic source code. Next, you compile it with asyn to detect to be able to detect this error. Then he Googled for graphics magic fuzzing corpus and downloaded to feed it into the image or graphics magic. And next we would use, he used convert tool to convert it to RGBA format. So this is purely 4 bytes of memory, which represents color at a certain pixel. And each 4 byte, actually inside this format, each 4 bytes represent a new pixel. So if you would go by 4 bytes, it would have RGB bytes, alpha byte, and that's it. So he used convert tool, and you can read about a send option that I would be describing this right now by using this link. I will describe it by words for you. So the option, actually, this is an environment variable that we would export here before performing conversion. Option is called malloc fill byte. Normally, when you allocate something by using malloc function, it leaves memory uninitialized. But if you are using calloc function, the memory is zeroed. So the trick here is to supply some option to the asyn, so it would fill byte just like calloc, but it would fill the memory allocation with this byte, which was supplied by us. So let's assume we would every picture we would convert several times. First of all, we would use this option by using malloc fill byte as 0. We would convert image, and each call to malloc would be filled. The result buffer of each call to malloc would be filled with 0. Next, we change this value to some other value. Let's say it's 128 as an example. And we convert picture one more time, but we name it differently, obviously. Let's say we are using another value and another value, just to compare different kind of values and how they look. We may actually use every one of 256 values, but let's just keep that a little bit reduced for now. And yeah, I have already told about this. So we hope to detect uninitialized memory error by using this RGBA format and just purely extract uninitialized memory from this image. But the last step that we would take, we would compare different images that we have converted. So the first image, let's say we converted it with malloc fill byte 0, and the last image we have converted with malloc fill byte to 155, and we compare results of these conversions. So if they are different, then the initialized memory has been used, and this leads us to idea that we should make look into the code and make some research where initialized memory of the allocated buffer has been used. So yeah, that's it. That's a trick, and that's a very private trick that I think that nobody but me and Emil previously known about. So yeah, coming back to the coverage guided fuzzing, after AFL came out, and it has grown in popularity, and all world was like this. Security engineers sometimes were saying that fuzzing is just dying and it's stupid, that you don't analyze the code, that you must read the code, and everybody in the world was, haha, IFL go, brr. Here I have some statistics as an example. So you can see that number of detected vulnerabilities since 2013, 2012 has been growing a lot, and I think this is partly due to the fact that fuzzing has grown in popularity a lot. So hopefully we would see decrease amount later on of this amount because a lot of bugs, a lot of software has been fuzzed to death already, and we would be able to find less vulnerabilities and more software would become more stable. But the question is here, how do you find memory corruption bugs in 2020? So I have two common strategies when I try to secure the software. Normally, I approach it in the way that if I would like to utilize fuzzing to discover some bugs in the software, I try to use these two strategies. So the first one is search where nobody was searching. As an example, I have already told you that this summer I have discovered 2 bugs inside the VirtualBox, and this place was obviously searched by many security engineers. So here I utilized the second strategy that is called fuzz like nobody was fuzzing, because I assumed that since I have found bugs with this approach, nobody has been fuzzing in this way, which is smarter way that the software has been fuzzed previously. So normally I would approach software with idea in mind that this software has been fuzzed already. I would try to make some research or make this assumption on my own, and you have to think that this software might have been fuzzed in this way. Let's try to enhance it. And yeah, that's my idea that I would like to stress upon. But let's say it is all good until you have some simple parsing software. In example, let's say you have a PNG picture. It would be quite simple for AFL-like fuzzer to detect this kind of this kinds of errors because it uses byte flip and bit flip mutations, and PNG is a binary format. But let's say we have some structured input, a highly structured input. As an example, I would say an IP packet, and let's say we want to fuzz a code which is used to defragment IP packets, and we have to generate several IP packets which somehow would result in invalid behavior inside the program. For this purpose, I would recommend using Libprotobuf-mutator, which is a tool based partially on libfuzzer and protobuf, as it comes from its name. So you can describe in protobuf what kind of data you would be using inside during your fuzzing process. You could describe its structure, and it would be easier for fuzzer to mutate this kind of data because in most times they would be valid in the terms of the version of IP packet would be valid and type of service value that you want to fuzz would be valid. But the reason why you use it here, that you want to fuzz actually fragment offset field, and you would tell fuzzer to use, or maybe you want to fuzz packet length or header length, and you would tell fuzzer that it is unknown value, but it's required in your packet, and it is some integer that you want to fuzz. So it would help your fuzzer a lot if you're using it to fuzz highly or find bugs in the code that is parsing highly structured input. So yeah, to read about more, I cannot recommend this page, which is called Structure-Aware Fuzzing. Libprotobuf-mutator, we have been discussing right now. Video by LiveWorkflow and Nedwill, which is about finding iOS kernel exploit. This is a success story about utilizing structure-aware fuzzing to find really severe critical bugs inside the software. And this technique is also used by syscaller. I don't speak about this fuzzer a lot because we have very limited time, but this is a really amazing tool as well. It is a fuzzer which is written in Go, and it is used to find memory corruption vulnerabilities inside Linux kernel. So it uses this technique as well. So I would recommend you to visiting it if you are very interested in it. By the way, I think that Linux, by this point, it came to the point that this syscaller fuzzer has found so many vulnerabilities inside the Linux kernel that Linux developers are no longer able to write patches for them. There are so many of them. Yeah, a really good tool. Last but not least, this is the technique that it hasn't been discovered lately, but I think everyone was so busy with rewriting their own version of AFL that this approach has been not widely discussed, and it is called snapshot-based fuzzing. Right now, it has become so much more popular. So let's assume you have some application that has a really complex startup routine, like VirtualBox, or it takes a really long time. As an example, Microsoft Word. You want to discover bug inside a Microsoft Word. So obviously enough, you want to target some parsing of the document and this is the only thing that matters inside this timeline, that your bytes are going through the parsing routine, and you want to detect errors inside this short amount of time. But startup actually is taking so long that you are not able to detect any that it takes really long, that you are not able to just supply this tool with documents or with some input, because it takes so much time, it won't be any efficient to fuzz it. So you take a snapshot inside this timeline of virtual memory and registers of this application, and you take this snapshot before first byte influences control flow of the fuzzer. So next, you inside this snapshot, you find your template of the data that you have supplied to your to this program. So, and you trying to run this program again inside your own hypervisor, and by you do it by finding and editing data in memory, and then you try to resume your program. So this is how the process of fuzzing works. You're inside your hypervisor, you just swap your template data with your fuzzing data, and you continue running. So this approach is coming more and more popular. It is widely discussed on Gamozo Labs YouTube channel, which I cannot recommend more. It has a lot of videos on fuzzing. I am in progress of viewing them as well. But there is so much content, it just can be depleted, because you have to analyze and memorize its content. So it's very, very long journey to view all these videos, even about snapshot-based fuzzing. So if you're seriously looking into it, I would recommend you to watch video about writing deterministic hypervisor, or Orange Slice, I think it is named. And there is a really good article if you don't like video content, you prefer reading, which is a hypervisor which is called Barbervisor, maybe because it is written in Rust in a hipster language, by Cisco. And I will show you, when I share your slides, you'll be able to click these links, obviously. So yeah, 2 points: long start time and complex application where it's hard to collect coverage. So this is where the snapshot-based fuzzing is really good. So now let's proceed with the takeaways. I think personally that best way to learn fuzzing is by reading source code. I cannot stress this more. Obviously, fuzzing is an arm race, and you want to have better equipment to find more bugs. But companies are actually building huge infrastructures for fuzzing, but still you want to write efficient and fast fuzzers as much as possible to run in, so you would be able to run them locally on your computer as well. Fuzzing is not a panacea. You still have to utilize other techniques to find more vulnerabilities. You have to find variants, you have to use static analysis, you have to apply manual analysis of the code, because sometimes fuzzing is just not working for some project. Yeah. There are some bugs that you wouldn't be able to detect by utilizing only fuzzing. As an example, the bugs that utilize 16 gigabytes of memory, you won't be able to detect those because fuzzing is a fast process. It is it should be working like in a certain amount of time. Every fuzzer should be limited in memory, and if you have this kind of bug in some server application which has like 16 gigabyte of memory, and application have to consume it all before it would be able to trigger the bug, then it obviously depends on the fuzzer, but probably you won't be able to detect it. Visualize your coverage. It is important because sometimes fuzzing can be really challenging. Your fuzzer cannot just pass some condition, and visualizing is important due to the fact that process of fuzzing is it is not as straightforward as some other concepts. As an example, when you're compiling a program, you want to sometimes decompile it to see how it is working on assembly level. And in case of fuzzing, you want to visualize your coverage to see how your fuzzer is efficient. And one of the last points that I like to make it, I think that that I'm really happy about that I'm working in this industry, because to be good at information security, you have to be good at almost every aspect of computer science. In this case, you have to be good in OS internals, in software development, to build these kind of tools like snapshot-based fuzzers. You have to be able to, you have to be good at compiler internals. If you want to build tools like libfuzzer, you have to be good at building distributed systems. If you would like to be able to run your fuzzers simultaneously on various machines, and etc., etc. So homework. So we didn't get very practical this time due to the limited amount of time, but I still would like to give you a homework. If you have become interested in the subject, or you were interested in the subject previously, so there are 2 points that I have made today: fuzz like nobody have been fuzzing, and fuzzing where nobody have been fuzzing. So today I would like you to apply those concepts by going to the Google OSS fuzz, by choose a project that you are familiar with, or you will get familiar with it, and learn about how fuzzer is implemented inside it, and think about ways to improve it, or what else can you fuzz to find a memory bug corruption in it. In 2016, I have applied this concept to find memory corruption bugs in FFmpeg, and maybe you would be able to do something interesting yourself as well. So this is it. Reach me out on Twitter. Here is my tag. Or in any other way, if you have questions, please feel free to ask. I think I have even used more time than I should, so excuse me please for that. And that's it for today. Thank you.